Welcome back. We left off in the last presentation talking about how Maxwell's four equations offer an elegant and complete classical description of the electromagnetic field. Now it's time to just take a brief look at something special that happens when you throw these equations together, mix it in with a little bit of math, and keep your eyes peeled for something that you may already be familiar with. So let's examine Maxwell's equations for the specific case of a vacuum. You're out in space, away from all matter, and that includes any charged particles. So the volume charge density here, rho, would be 0, and the electric current density would also be 0. So we get rid of those. We wind up with this set of equations, and this is like the three-dimensional generalization of d dx. This is like saying d dx of the electric field is 0, which would actually be what? That's like saying the slope is 0, slope in space. So in other words, the electric field, I don't want to say it's not changing in space, but its divergence is 0. We talked about how if the E field appears to be diverging from a point, then there has to be charge at that point. Well, in this case, it's not diverging because there's no charge there. And we have this relationship between the way E is changing in space and the way the magnetic field is changing in time. The next step one would take to get to the result that we are seeking here is to take a three-dimensional derivative of both sides of this equation. So we take the curl of both sides. If you haven't yet studied vector calculus and you don't know what that means, it's a lot like just taking the derivative of both sides. And when you take the curl of the electric field, you get a more complicated expression. You would look it up in a table of vector identities. If you've taken vector calculus and you're familiar with the divergence, curl, Gauss's theorem, Stokes' theorem, and you'd like to see the details of this process, send me an email and I'll hook you up with some notes that shows the whole thing, I think, in great clarity. After going through that process of taking the derivative of both sides, really you take the curl, which is like a three-dimensional derivative, you wind up with this equation here. Now this triangle squared, that's called the Laplace operator or the Laplacian, and it's really a generalization to 3 dimensions of a second derivative with respect to position. We've seen this a lot already this semester when we looked at waves on a string. So here we've got the second derivative with respect to all 3 space variables and we add those up. That's what's going on here. So if we take this term and put it on the other side, it should be familiar. Remember a couple weeks back when we used Newton's law to analyze the dynamics of a little piece of string, a little segment on a larger length of string or longer length of string. And we ended up arriving at this equation right here, which we called the wave equation. It related the second time derivative of some quantity. In this case, it was the vertical displacement of the string. We related that second time derivative to the second derivative with respect to position and concluded after our study of progressive waves that this term right here, tension over mu, must be the square of the speed. Remember that the speed on strings is the square root of the tension over the mass density. So let me rewrite this as speed squared. And then we could, of course, put the speed squared on the other side and write the equation like that. That's another way of writing the wave equation. Try to memorize that, at least for the next 10 seconds, so you'll recognize what we're about to see on the Wikipedia page. You have the reciprocal of speed squared in front of the time derivative. And that's exactly what we're looking at here. Well, I guess I should start with this one. We've got some constant. We know that these are experimental constants, the permeability and the permittivity, out in front of the second time derivative. And if you put this on the other side, it looks just like the wave equation on a string. The only difference is instead of just d dx squared with respect to x, well, that's redundant. Instead of just a second derivative with respect to x, we have second derivatives with respect to all space coordinates. This is the wave equation. That's what we're looking at. So immediately we recognize there has to be some sort of wave behavior associated with electric and magnetic fields. And in case you missed it down here, I'm identifying, this is what the Wikipedia page is doing. As I just showed you for waves on a string, the coefficient in front of the second time derivative is 1 over speed squared, whatever constant shows up. For the wave equation on a string, that constant would have been mu over the tension because it's 1 over speed squared. In this case, it happens to be the product of these experimental constants relating to the strength of the electric field and the strength of the, I should say, the strength of the interaction between charges and the strength of the interaction between current carrying wires. So let's give that speed a special name. Instead of calling it V, we'll call it C. And of course, you see where this is going, but pretend you don't for now. Well, I showed you in the previous presentation how to deduce the dimensionality of the permittivity here. Just by looking at Coulomb's law, you can conclude that this quantity here must have units of newtons, meters squared over Coulomb squared. Epsilon naught is in the denominator, so take the reciprocal of that, and we wind up with Coulomb squared over Newton meters squared. Also, I'm not totally sure that this is the letter epsilon. It sure looks like the Greek letter epsilon. There's another one that doesn't have the curvy humps. Here are the units of epsilon naught. And we've also seen that mu naught is given the exact value 4 pi times 10 to the negative 7th. And here are the units of mu naught. So I'm just reminding you about something that we've already done. Since we know the numerical values and we know the units, we can check that the quantity just shown on Wikipedia does indeed have the units of speed. And then let's take a look at what the actual numerical value of that speed would be. If there are such thing as waves involving electric and magnetic fields in vacuum, what is the speed at which they should travel? We've spent enough time this semester studying progressive waves and the simple math that we can use to describe them, these sinusoidal progressive wave functions. We should be convinced that whatever number pops out is the speed at which these waves propagate. And here's something worth memorizing. The product of those two ubiquitous constants. I say ubiquitous because they show up everywhere in the study of electricity and magnetism. That product is equal to the reciprocal of the square of the speed of light. You don't have to memorize that, but if you do, it will give you some facility with the many formulas that we encounter in this chapter. Okay, let's turn that around and solve for C. Remember, we identified the letter C with the speed at which these signals or disturbances should travel. I almost said travel through the medium, but we've already looked at the fact in a previous chapter that perhaps there is no medium necessary for electromagnetic waves. Okay, plug in the values that we just looked at. And if you only do this once in your life, seriously, I encourage you to whip out your calculator and actually do this yourself. Plug those numbers in and see what pops out using whatever you've got at home, whether it's an old Soviet era Casio or an abacus. I'll just hang tight while you do that. And sure enough, the number that pops out is familiar. Now, this number is not exactly the number for the speed of light quoted here, and that's because I used just these 3 significant digits in my calculation. The permittivity of vacuum is known to many more digits than this, but I don't know how many digits were known to Maxwell, who was the first to do this calculation back in the 1860s. So if you plug in these numbers, you get something out like this, which is awful close to the experimentally known speed of light. Whoa. So you probably knew where this was headed, but try to appreciate what an earth-shattering realization this may have been to somebody 150 years ago when it was first discovered that electric and magnetic fields should support some sort of wave phenomenon, perhaps even in vacuum, no medium necessary, although that wasn't clear at the time. And the speed at which those waves travel just happens to be the same as the speed of light. Can't be a coincidence, right? Light must be an electromagnetic wave. Here's some fun numbers. I have this one memorized. It takes about 8 minutes for light to get from the sun to you. So every time you go outside and see the sun or bask in the light of the sun, there was an 8-minute delay there. Any distance you're talking about, there's a delay. Even when you look at yourself in the mirror, it took a little bit of time for the light to bounce off your face, hit the mirror, and come back into your eye. So if you ever look in the mirror and you think, gee, I look a little older today. Well, you're actually even older than you look, because you're at least, what, a couple nanoseconds older? That's how long it took the light to get from the mirror to your eyeball. You can find plenty of information about the historical background on Wikipedia and elsewhere. So it's been a while now since this was discovered. I said 150 years, I guess it's more like 160 now. And Maxwell recognized immediately it's got to be more than just a coincidence that these electromagnetic waves travel at the same speed as light, because that speed had been measured, probably crudely, but it was known to physicists of the day. And you'll notice here, he's talking about transverse undulations of the medium. So back in the 1860s, anybody who was familiar with this possibility for electromagnetic waves was still limited in their thinking that light required a medium. I mentioned in a previous presentation, it wasn't until the 1880s, 1890s that scientists really began to probe that question, whether or not a medium was necessary. Oops. And you can also see that the value for the speed of light he obtained was a little on the high side, because we know now that it's closer to 300 million meters per second. He got something like 311 million meters per second, it looks like. There's the exact value. If you're curious, you don't need to know this number. And I say exact because the second is now defined ultra precisely using atomic clocks. I mean, there's an insanely precise definition of the second, which we don't have time to talk about. And we now take this to be, by definition, the speed of light. So what that really does is define the meter. By taking this to be the exact speed of light with a very precise definition of the second, we have now defined the meter. One more fun number when it comes to the speed of light. It takes light a little over 3 nanoseconds to travel 1 meter. A nanosecond is a billionth of a second, right? Much shorter than the blink of an eye. So 1 meter, that's a little over 3 feet. In fact, it's about 3.3 feet. So if light travels 3.3 feet in 3.3 nanoseconds, how convenient. It travels about 1 foot every nanosecond. That's a really cool number to remember. It takes light 1 billionth of a second to travel 1 foot, which tells you why, if you want your computer to be really fast, it's got to be small. Back in the 1980s, the 1970s, they were still making sci-fi movies with giant computers because, well, I'm sure computer scientists were aware of this, but maybe the general public was not aware of the fact that if your computer is the size of a room, it's going to take several nanoseconds to retrieve information from, let's say, the hard drive and get it over to the processor if they're in different places. So you need everything to be close, because even light takes a finite amount of time to get from A to B. It's also the reason why you can't necessarily play, like, if Elon Musk and NASA and the European Space Agency, if we succeed in putting people on Mars, if one of your friends becomes an astronaut and goes to Mars like a crazy person, you are not going to be able to play online games with them, because it just takes too long for light to get from here to Mars. I think a previous graphic said it takes something like 10 minutes. In order to play a game in real time over the internet, you need a latency of something like milliseconds. Isn't that remarkable that if you're in the Los Angeles area, you can play with somebody, let's say in the Chicago area, and it only takes a matter of milliseconds for the information from your Xbox, let's say, to go to some server and then perhaps go out to, your friend's Xbox in Chicago. So if you've ever wondered what ping is, it has to do with that latency, the amount of time it takes on electromagnetic signal to travel. Well, let's see, it's got to travel down possibly Ethernet cables in your home, maybe some more cabling like fiber optics across a city. There may be a microwave length, so at one point it may actually be traveling through air. Now I say electromagnetic wave because even though right now we're talking about waves in vacuum, it doesn't have to be vacuum. The signals that you send down copper wires are also electromagnetic waves. In this case, they're actually traveling through a medium, but the medium is not necessary. And I mentioned in a previous video that the speeds are comparable. The speed of an electromagnetic wave down a copper wire, let's say it's something like 2/3 the speed of light in a vacuum. So light travels through copper wires. That's an odd thing to hear at first, because when you hear light, you think of something that can actually enter your eye. How can you put your eye into copper and see the wave? Well, you can't, but it's still the same phenomenon. If you watched the recent landing of the Perseverance rover, again, you may have thought you were watching live, but that's debatable. Can you really watch it live? It takes several minutes, maybe 10 minutes for that video feed to make its way from Mars to planet Earth. It did so at the speed of light. That's as fast as you can get. It's pretty darn fast, but not instant. Not long after Maxwell proposed that these waves should exist, and I imagine not every physicist was convinced by his reasoning, although he was well respected at the time. So that was 1862. It took another 25 years, thereabouts, for somebody to actually demonstrate these waves in a laboratory, to create electromagnetic waves. And that guy's name was Heinrich Hertz, not the ketchup Hertz, but the Hertz as in cycles per second. That's where we get that unit name from. And you can look up pictures of his original apparatus. You're looking at it right here. Some of this might make a little more sense if you had taken electromagnetism, but this is all ancient technology now. Here's a close-up of a piece of the apparatus. In fact, right here. So let's zoom in on that. I'll let you read through this later, but when you read this description, at least when I read it, it sounds an awful lot like our description of musical instruments, where when you buzz into the mouthpiece of a trumpet, you're creating noise, and that noise travels down the tube. It reflects at the bell of the trumpet because of the discontinuity with the air pressure or whatever. And most of those reflected waves interfere destructively, but certain frequencies interfere constructively, and you get standing waves. Here, it's a very similar phenomenon. He created sparks across this spark gap, and those sparks probably involved electromagnetic noise, which is a broad spectrum of frequencies. And those frequencies would have traveled down the wires as electromagnetic waves, but only certain frequencies would reinforce themselves or resonate. And so he set up standing electromagnetic waves. And we'll see later that as long as you've got oscillating electric charge, think of the electrons that are free to move around in a conductor. If those are oscillating at a fixed frequency, well, they're jiggling back and forth, they're accelerating. All it takes to create electromagnetic waves is the acceleration of electric charge. And this happened, like I said, something like 25 years after these waves were predicted. And this is the best part. I love this. This always makes me smile when I think about it. This guy, this brilliant physicist, was a little thick when it comes to entrepreneurship. He even had students prodding him like, hey, can you do something with these waves? There's got to be some practical application. And he just wasn't very imaginative when it comes to business. Yeah, I've heard other quotes that were even more blunt, like, yeah, I don't see any practical use of this. And that just sounds ridiculous to our modern sensibilities, because our entire lives seem to revolve around wireless communication at this point. I mean, you're watching this on your phone or your computer, all of which depend on electromagnetic waves. Okay, so it took this guy, Marconi, to step in and take advantage of the opportunity that Hertz passed up. Of course, Hertz unfortunately passed away at, I think, the age of 36. Maybe if he'd stuck around a little bit longer, he would have realized he could have made a ton of money off of these electromagnetic waves, but that's what Marconi did instead. Isn't it amazing to think how rapidly this all happened? 1862, after 100 years of struggle to write down mathematically the laws describing electric and magnetic fields. Maxwell was the first to do it. And I was reading on the Wikipedia article, you can actually pick up his original treatise on electromagnetism. He used a set of 20 equations to describe the field laws. And it took another physicist named Heaviside to clean those results up and express them using our modern vector calculus, because it's really not that difficult to understand them once you know what divergence and curl are. In the form in which Maxwell wrote them, that they were a little more inscrutable. But as soon as he wrote those down, 1862, within what, 30 years, people figured out how to create a new technology out of this natural phenomenon, you know, to harness the power of wireless communication. And you know, the rest is history, as they say, and we all kind of know. A few decades later, TV came along, and then, well, many of you were born after the internet was created, but all of this stuff happened in the last 150 years. And Marconi began with making wireless transmissions between ships at sea. I think that was the first application. And before long, he was able to send signals clear across the Atlantic Ocean. The hats here, definitely the secret to their success. Okay, and now we arrive at a small number of important properties of electromagnetic waves in vacuum. Everything we know about E and B fields can be obtained from Maxwell's equations. That's where you go. That's the authoritative statement about E and B fields. How come this GIF stopped? There we go. Okay, so you can use these equations to show, and we're not going to show it, we'll just list the results. You know what, maybe before I list them, we should actually look at the GIF here. What's happening? You can see that there's a wave traveling forward, and you'll notice there's a red vector representing the electric field at a particular point in space. So this animation is only showing the E and B fields at that one point. You see that the electric field is oscillating transverse to the direction of travel of the wave. Right? So that was mentioned earlier in the semester, that the electromagnetic wave is a transverse wave. Same thing for the B field, right? It's also oscillating transverse to the direction of propagation. The direction of propagation, that's just another way of saying the direction that the wave travels. I also notice in this GIF that E and B are oscillating perpendicular to one another. So they're both transverse. That means perpendicular to the direction of travel of the wave, but they're also perpendicular to each other. I will also note that they are oscillating in phase. They're each growing together and then shrinking together. It's not like as one is growing, the other one is shrinking. So they're oscillating in phase. And while you can find all sorts of simulations like this one, you do have to use a bit of your imagination to really understand what's happening here. This is what's called a plane wave. So can I stop the GIF? No, it doesn't stop when I want it to stop. Imagine a plane piercing this axis. This would have to be the y-axis since we've got the x and z axes here. So here's the y-axis. That means the wave in this particular simulation is traveling along the y-axis. Imagine a plane that's piercing the y-axis and perpendicular to it. At every point on that plane, the electric field and the magnetic field are doing the exact same thing that they're doing here. So you can't represent that really in a picture because it would be way too cluttered. But imagine any point on that plane that's cutting through the y-axis right here. The E and the B fields are doing the same thing everywhere on that plane. I'll have more to say about that when we look at another simulation. Here's the first observation about the relation between the E and the B fields for electromagnetic waves in vacuum. It's important to understand this condition that E and B are perpendicular. It's not always satisfied. You can easily produce a charge configuration or set up a charge configuration and a current distribution such that you've got E and B fields that are parallel. We're talking here about electromagnetic waves in vacuum. For those waves, E and B are perpendicular, and you can see that in the simulation. You could say they're mutually orthogonal. This second statement tells us that both of those fields are also perpendicular to the direction of propagation. So I'm going to use this commonly used letter K, K hat. That's a unit vector that points in the direction that the wave is traveling. K hat. E and B are both perpendicular to K hat. That's really just another way of stating that it's a transverse wave. Both quantities, the electric field and the magnetic field, are oscillating transverse. So now we have the answer finally to what is waving in an electromagnetic wave. For water waves, it's very clear that it's the surface of the water that's waving up and down. Waves on a string, the string itself is waving. Sound waves, it's the air oscillating back and forth. That one's a little more difficult to picture because it's a longitudinal oscillation. But in the beginning of the semester, it may have been a bit of a mystery to you. What's waving in an electromagnetic wave? Well, now it's very clear. It's the electric and magnetic fields which are oscillating. Here's the last one that's not obvious from the equations and definitely not obvious from the animation here. The strength of the E field in SI units is 3 times 10 to the 8th as great as the strength of the B field in SI units. So in the SI system, we measure electric field in newtons per coulomb. We measure the B field in Teslas. Well, whatever this number is for the electromagnetic field or for the electric field strength, it has to be 3 times 10 to the 8th as big of or I should say bigger. You multiply by 3 times 10 to the 8th. So it's a much bigger number than the number that describes the strength of the B field in Teslas. And that's really a consequence of our system of units. There are older systems of units where people who deal with electromagnetic fields often, it depends which branch of physics you're in, but there's another system in which E and B have the same strength in an electromagnetic wave. So it really depends on your system of units. But in SI, E is the much bigger number, and the ratio between them is the speed of light. There's one more observation we can make. Yes, both fields are perpendicular to the direction of travel, and they're perpendicular to each other, but there's a specific spatial relation that's captured by this equation. This is the cross product, of course, E crossed with B. And what I've done here is E hat. So I'm really talking about a unit vector that points in the direction of the E field and a unit vector that points in the direction of the B field. You would have to use the right-hand rule to visualize this. So I like to use this particular right-hand rule. As I've mentioned, there's various ways to use your fingers or your hand to see the right-hand rule. I like to put my 4 fingers parallel to E, curl them towards the B field, and then my thumb tells me the direction that the wave is propagating. Remember, K hat tells us the direction that the wave is propagating. So I should point out that this K hat is not the same as the unit vector that points along the Z axis. Oftentimes we like to use I hat, J hat, and K hat for unit vectors along the X, Y, and Z axes. This is something different. This is a letter that's commonly used in physics to represent really the flow of momentum, the direction of momentum flow, because we're going to see that electromagnetic waves also carry momentum. Okay, so see if you can do that with your right hand. I wish I could pause the GIF, but put your 4 fingers of your right hand along E, curl them towards B, and you'll find that indeed your thumb points in the direction of wave travel. That's something you should practice with a couple examples. That's the way electromagnetic waves work in vacuum. And we know that because of Maxwell's equation. We also know it because of experiments. First, a word about plane waves. This is from the Dan Russell website. Let's consider this animation to be representing a traveling electromagnetic plane wave. So rather than actually showing you the profile of a string as it oscillates transversely, the height of the curve here, as seen from the side, would represent the electric field. So where the curve peaks, you're talking about the maximum of E field. That's when the vector is pointing up, let's say, with the greatest length. And then the valleys here represent the E field pointing the opposite direction with the greatest magnitude. And hopefully what this animation is helping you to see is that it doesn't just show you, or the electric field doesn't have a particular value just at one point in space. If you go back along, like the rib here of this surface, it's got the same value all the way back. So this animation takes you part of the way to understanding what a plane wave is. What it doesn't show you is the fact that if you go straight up, then the wave has the same value at every point along that line as well. It's actually kind of difficult to describe a plane wave because I haven't found any animation yet on the web that really makes it easy to see. Here's a better representation of an electromagnetic wave. We see that the E and B fields are perpendicular. They're also transverse to the direction of propagation, and they're also oscillating in phase. So just park yourself at a particular point on the axis of travel and imagine you're a proton. That's a silly thing to imagine, but if you were a proton, you would be pushed by the electric field. Let's call that the green vector. And you can see as the wave passes by, you're being pushed up and then down and then up and down. So you're oscillating in time. It's like we said for progressive waves for strings as well. Not only can the wave be sinusoidal in space, like if I were to pause this, you can see a sinusoidal dependence on position. But if you look at how the electric field changes in time at a particular point in space, it's also changing sinusoidally in time. So a sinusoidal progressive electromagnetic wave has a sinusoidal dependence of the electric field on position, but also a sinusoidal dependence of the electric field on time if you put yourself in a fixed position. Here is a Falstad animation of plane waves. I think this helps. Think of the green bars as representing the peaks, and the red bars are the valleys. So the wavelength would be the distance from one green bar to the next. And this makes it easier to see that the phase of the wave is constant across a bar. Remember when we talked about the phase on a string, for a progressive wave, and we said that the peaks had phases of 0, 2 pi, 4 pi, etc., and the valleys had phases of pi, 3 pi, 5 pi, etc. We'll just pick one of these green bars, and let's say that the phase everywhere along that green bar is 2 pi, and then the next bar has a phase everywhere of 4 pi, etc. So the phase is constant vertically across the screen. And then the last dimension that you have to add in your imagination is coming out of the screen. Imagine this green bar, first of all, extending forever up and down, but also coming out of the screen and going into the screen. That plane that I'm describing would have the same phase everywhere. So whatever the wave is doing at one point on a green plane, it's doing everywhere on a green plane. I think this one makes it a little easier to conceptualize a plane wave. Let's take a look at another simulation from the Falstad site. I'm here on the home page, well, the math and physics page of the Falstad website. I'll start with 2D Electrodynamics Applet. This TE here, I believe TE stands for transverse electric field. Before we even mess with this, let's check out the directions. What is Mr. Falstad telling us? Okay, so we've got a source emitting waves. The color indicates the magnetic field, okay? So where the field is green, that tells us that the value of the B field is positive, and it says towards you. So coming out of the page, where it's red, the magnetic field would be going into the page, or I should say into the screen. So the arrows that you see tell you the direction of the electric field. Now, since this simulation was called electromagnetic waves TE, presumably for transverse electric, any vector pointing in the plane of the screen, that would be considered the transverse direction. Am I getting that right? I guess that makes sense because it looks like this wave is traveling to the right and all of these arrows are up and down, which would be transverse. Okay, let's go to the full screen. And let me switch over to oscillating dipole, because that's the simplest one to understand. So what are we looking at? A dipole, remember, is a negative charge and a positive charge next to each other. And we're told that this that this dipole is oscillating. So just think of the positive and negative charges as switching positions. Yeah, it's not real clear here with the labeling, but you've got a plus sign on top, let's say, and a minus sign on bottom, and they're switching positions. That's what it means to have an oscillating dipole. Now, if the charges are bouncing around, then they're certainly accelerating. So here we see an example of how accelerated electric charges emit radiation or electromagnetic radiation. That is the source, ultimately, of electromagnetic waves, at least in the classical picture, oscillating or accelerating electric charges. So we see that there's a disturbance in the field moving outwards. The B field is changing. You can see the colors changing. Remember, the green and red colors show you the peaks and the valleys of the magnetic field. And then the arrows everywhere on the page represent the electric field, and they're obviously changing as well. Let's try increasing the resolution here. Okay. If I clear the fields, so right now it's as if nothing's happening. These charges are not moving. And when I put them in motion again, you'll see it takes a certain amount of time for the signal that they create to travel outwards. It's not like the information about the change in position can instantly appear over here. Like if you're hanging out over here and you'd like to know about the changes going on here, when those changes happen, you don't immediately know that they happen. It takes a while for the update in the electric field to get to you. You can imagine that there's a static electromagnetic field around these charges, or it would really be a static electric field. And when you change the configuration of the charges, the entire field has to update. But that update doesn't happen instantly. It ripples outwards at the speed of light. And so there's a finite transmission time between changing the configuration of the charges and a person over here actually detecting that change. See that? It takes some time. If that were not true, then you would be able to transmit information instantly from point A to point B across any distance, which doesn't jive with our common sense, our modern common sense. Can we relate this to the content of Maxwell's laws or Maxwell's equations? Remember that the equations related the curl of the electric field, which is basically the change in the electric field with respect to position. It related that derivative to the time derivative of the B field. So if the magnetic field is changing in time, then the electric field must be changing in space. There was another equation that said the converse of that, that any change in the electric field in time would cause the magnetic field to change in space. And that's kind of what you're seeing here. Just focus on any one of these arrows. You see that the electric field is changing in time. And at that same location, there's a change in the magnetic field in space. So where there's one, you find the other. Now, it's not obvious how those two statements immediately suggest sinusoidal waves, for instance. You kind of have to look at the math to see that, but hopefully those remarks make it plausible that you should be able, that empty space should be able to support traveling electromagnetic waves. I've gone with a different setup here, the half-wave antenna. Think of this as a short segment of conductor, and the charge carriers inside the conductor are electrons, So you've got that electric charge oscillating back and forth. Again, that's accelerating charge. Accelerated charges emit electromagnetic waves. And it's not too difficult to see how you could send information this way. Of course, all of our information in modern times is sent via electromagnetic waves, nearly all of it. Cell phones, fiber optics, television, satellite, all that stuff. Just think of Morse code. Sending information with Morse code is as simple as making a sequence of beeps. Beep, 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 beep. You know, those beeps represent letters. You could do the same thing with these. Think of the electric field as being like the beep. If the electric field is pointing up, that's like the tone being on. And if the electric field points down, the tone is off. So if you could somehow encode the beeps, so to speak, into the oscillating electric field, you could send information that way. That's super basic. You know, in the last 150 years, people have figured out much more ingenious ways of putting information into electromagnetic waves. But as long as you can change the field and time, you can put information into it. Let's look at one more here, reflection at a conductor. We see that it reflects. So all of these simulations are based on the actual physics. If you were to look at the source code, you would probably find Maxwell's equations within them. It wouldn't be obvious, but whoever programmed this, probably Falstad, made sure that the time derivative of the B field is related to the space derivative of the E field in the manner prescribed by Maxwell's equations. So if you take a course on electromagnetism, you may learn a little bit about the boundary conditions here and how an electromagnetic wave should partially reflect at a conductor. Here's the one called the TM simulation from the same homepage. This is the plane wave setup. See if you can figure out right now. Oh, I should provide a little bit of background information. If you read the instructions for this one, the arrows now show you the magnetic field. See how everywhere in this green bar, the arrows point to the right. Here they point to the left. That's like the peaks and the valleys for the magnetic field. Now the wave is clearly traveling down the page. Can you figure out which direction the electric field would point? Of course you can. Use the right-hand rule, use the spatial relationship between the three vectors that I showed you in the graphic, and you can see that the electric field has to be pointing out of the screen or into the screen. So let's think of green as being out of the screen. Actually, I could check that with the right-hand rule, and I'm getting that backwards. So the green represents the E field going into the page. If I put my forefingers of my right hand into the screen, and then I curl them to the right, which is the direction of the magnetic field, my thumb ends up pointing down the screen, which is the direction of propagation. So green means E field goes into the screen, red means E field's coming out of the screen. Here's yet another way of visualizing a plane wave. This one's pretty good. What else do we have in here? Waves emitted by an oscillating current in a loop, so like a loop of wire. That's a particular type of antenna. Let's take a look at this one as well. Magnet pair. And by the way, if you try to do this on your own, I wasn't able to get this to work in the full screen mode. What just happened there? Well, here's how I would think about it. You notice those pulses that emanated from the locations of these magnets. Let me do that again. So I have to go back to a different setup. Watch what happens when I switch to magnet pair. Okay. I think the simulation is written so that you can think about it this way. Imagine empty space, nothing there, no electric field, no magnetic field, and suddenly these magnetic dipoles are put into place. And if a field appears where there was none before, then that means the field is changing. And Maxwell's equations tell us that if there's a change in the B field, there's got to be a change in the E field. So that disturbance propagated outwards because there was something changing in time. Now, right now it's all static. Nothing's changing. Here, I believe we're looking at the magnetic field. Yeah, this is the field of a magnetic dipole. You can see those closed loops of the field lines coming out of the North Pole, swooping back in through the South Pole. But watch what happens if I just grab one of these little domains and change the direction. Do you see that ripple that travels outwards? Anytime the local field at a point changes, whether it's the B field or the E field, you're going to get that disturbance that travels outwards. Because where there's a change in electric field, there must also be a B field. Where there's a changing B field in time, there must also be an E field. I don't want to say that one creates the other, because in my view, it's ultimately electric charge that creates those fields in most cases. But if that's how you want to think about it, because it helps to think about it, fine. But you do want to understand that any change in a field in time is going to create a wave that travels outwards. Now, here's the really profound thought. What if your eyeball was up here in the upper right corner? If I start making changes, well, let me go back to the half antenna example. I have to find that. I'll go with the oscillating dipole instead. So imagine that your eyeball is up here in the upper right part of the screen. Let me clear the fields. Right now, there's, if there's a positive charge here and a negative charge, what we call an electric dipole, then there's going to be a static electric field around that dipole. And you can look up what that field distribution looks like, but it's static. It's not changing in time. So there's no flow of energy away from the dipole. There's no energy flow associated with the static field. But as soon as I put these charges into motion and get them accelerating, the field around them has to change, and that change will ripple outwards. And go back to imagining your eyeball right here. What do you think you might perceive as that ripple passes your eyeball? Right about now. Well, it depends. It depends on the frequency. If the frequency is, let's say, 1 million cycles per second, I'll represent that with this simulated frequency. If the oscillations are happening 1 million times a second, then as that energy passes into your eyeball, you're not going to notice anything. It looks like my computer's freezing up here. Yeah, you won't detect anything if the oscillations are happening 1 million times per second. However, if those oscillations are on the order of 10 trillion to 100 trillion, your eyeball will detect it, and we call it light. So that ripple traveling outward through the field, that ripple that carries the information about the change in the configuration of the charge, that ripple is light, and the energy that it carries away is light energy. In the modern interpretation, we would talk about little packets of light energy being absorbed one at a time by your retina, and those are called photons, something we'll talk briefly about towards the end of the semester. What we're describing here is the classical picture of electromagnetic fields. And classical isn't to say that it's wrong, it's just to say that the scope of applicability is somewhat limited. So there are things about light that you can't necessarily explain with this model, but there's an awful lot that you can. So it's not untrue to say that light is this outward traveling ripple that results from accelerating charges. Again, the electric field in the vicinity of the charges depends on the configuration of the charges. If you change the configuration of the charges, the field around them has to update, but that update cannot happen instantly. If it could, you could use the positions of the charges to send information instantly. So it takes time for the information about that updated configuration to travel outwards. And that information, as it traveled outwards, that is light. Of course, it's information, right? When you receive light in your eyeball, there's an incredible wealth of information that you're getting from your environment. There's an important quantity related to the E and B fields that we now need to take a look at. And with the benefit of hindsight, see, I know where this is going. I'd like to look at this quantity here, the product of the electric field and the magnetic field divided by the permeability. And let's start by just looking at the dimensionality of this quantity. We've already reviewed the units of mu naught. This is actually the units of the reciprocal because we're looking at 1 over the permeability. C is for Coulomb, S is for second, N is for newtons. So we've got charge squared over force time squared. Well, those of you who haven't taken electromagnetism may not know this, but the units of the electric field are newtons per Coulomb. I did emphasize in the last presentation that the electric field tells you the force that would be applied to a second charge placed at a particular location in space. So it's the force per unit charge, newtons per Coulomb. Let's quickly figure out what the units of B are. We know that the magnetic force on a charge moving with speed v in a magnetic field B is QVB. So we can deduce from this equation what the units of magnetic field must be. They're Teslas, but what is a Tesla in terms of more fundamental units? Well, if we want newtons to come out, charge has units of coulombs in the SI system, speed has units of meters per second, and so we can infer or deduce, whatever the right word is, we need newtons to come out, we need to cancel the seconds down here, we need these meters to cancel those meters, and these coulombs to cancel those coulombs. You don't need to memorize this, but evidently from this equation, those are the units of the magnetic field. So let's plug that in here. Does anything cancel? Yeah, a lot of stuff cancels. I've highlighted here everything that does cancel. Everything in red goes away. Coulomb squared. This second cancels one of these seconds, and the newtons cancel. So we're left with only Newton over meters over seconds. Newton over meters second. What the heck is that? It's not obvious, but watch this. Let's multiply on top and bottom by meter. So I introduced a meter up top and I brought another meter into the denominator. What's a Newton meter? Force times distance? Aha, that's work or energy. So we're really looking here at a joule. I'll make that substitution. And then what's this? Joule per second. That's the rate of energy consumption or production. 1 joule per second is the SI unit of the watt. Let's make that substitution. And now we're looking at something we recognize. This is, of course, why I chose these quantities. Watts per square meter. That tells us the concentration in space of power. How spread out is the power over a surface? In other words, intensity. This is a quantity we've already looked at this semester. The concentration in space of power, the flow of energy. Now, you're not going to believe this, but there's a name for this quantity. We'll see it's a vector. It's actually a vector that points in the actual direction of energy flow. We've already established the fact that electromagnetic waves carry energy and that the flow of energy is perpendicular to E and B. Well, there's a vector that we're defining right now that points in the direction of energy flow, and it's named after a physicist named Poynting. How perfect is that? I mean, did he have a calling? Was it fate for him? Did he choose his mission in life or in career based on his last name? I can't think of any better example of this that I've ever heard of in the history of science, but John Poynting is the one that figured out there's this vector. We call it S. Well, we call it the Poynting vector, but we use the letter S. And the dimensionality of S is watts per square meter. I did some reading about this guy. He authored, along with somebody else, a really popular textbook. It was basically like the Randall Knight Physics for Scientists and Engineers 4th edition of the early 1900s. I guess this book was really popular for, from what I read, the first third of the 1900s. Anyway, this guy also has been credited with coining the term greenhouse gases or greenhouse warming. Okay, so he's not just famous for his last name. Let's recast this equation in a slightly different form, because you'll recall that the reciprocal of the square of the speed of light is the product of these experimental constants. If we solve this for the reciprocal of mu naught, we get this. I'm going to plug that in right here. That's another way to think about the Poynting vector. And I'll go ahead and say right now, I would just memorize this one. We're coming up on a third or fourth way, I forget, to write this that might also be worth memorizing, but try to memorize this one. Here's where I'll recall that for electromagnetic waves in vacuum, B is simply related to E. Remember this relation? In magnitude, the magnetic field is described by a much smaller number than the electric field. That's just a consequence of our system of units. So let's substitute. Instead of B, we'll put E over C. That would cancel one of these C's. And here's the other way that's possibly worth memorizing for the Poynting vector. Poynting vector. Now, the Poynting vector isn't just associated with electromagnetic waves in vacuum. You can always define a Poynting vector in terms of E and B fields, no matter what those fields are. So this equation, where I went from B to E over C, this is only applicable for electromagnetic waves in vacuum. This one's always true, at least in magnitude. This one is only applicable for EM waves in vacuum, which is what we're talking about anyway. Here's the vector form. You have to use the cross product. So the full vector form of the Poynting vector tells you not only the magnitude, but also the direction. So let's go back to the graphic that we looked at already. E crossed with B gives you a direction along what I was previously calling K hat. Well, that actually is the direction of the Poynting vector. And here I've left off the vector symbols. This is kind of sloppy. Excuse me, because the graphic I found on the web just had E and B without the vector symbols. But when you see that cross product, you know you're talking about two vectors. All three of these are vectors. Okay, so rather than call it K hat, maybe you should be more attached to the letter S. The Poynting vector points in the direction of the wave travel, and that also happens to be the direction of the energy flow, which isn't surprising. That's kind of intuitive. And what you should try doing in your mind is confirming. If you look at the direction of E and B here, use the right-hand rule to confirm that the direction of the Poynting vector is the direction given by this purple arrow. That's true at any point in the oscillation. It's true right now, but also now when the fields are pointing opposite. In each case, if you use the right-hand rule, you'll find that S points forward. So E is flipping directions, B is flipping directions, but S does not flip directions. S is always pointing in the direction that the energy is traveling, which is the direction that the wave is traveling. Okay, Poynting went further than that. He didn't just, make up this vector and attach his name to it. There's a really profound statement that it can be derived from Maxwell's equation. So it's not a new result, really. It's like a reformulation of the existing theoretical framework there. Here's what it says. Let's use the capital letter U to represent all of the energy inside this box associated with electric and magnetic fields. If you take a class in electromagnetism, you'll learn the actual formulas that associate an energy density with each field. Anytime there's an E field in space, there's energy at that point in space. The same goes for a magnetic field. That shouldn't be surprising because it's like if you've got a toaster on high and you yank the cord out while the toaster is in operation, sometimes you'll see a spark at the wall. Anytime you have strong currents flowing, you've got strong magnetic fields in the vicinity of those currents, and there's energy associated with those fields. It's got to go somewhere when you pull the cord out of the outlet. So if you're looking at all the energy inside the box, that energy might be increasing or decreasing in time, and that rate of change can be calculated by looking at the flux of the Poynting vector over the surface. So right now, I'm imagining that the Poynting vector at all points on the surface of the box points into the interior. The Poynting vector points into the interior. And since the Poynting vector gives us the direction of energy flow, this picture suggests that the total energy within the box should be increasing in time. It's going up because energy is flowing into the box. That's a pretty intuitive statement, but it's remarkable that we can actually calculate that rate of flow just by combining the electric and magnetic fields. So du dt, that's the rate of change of the total energy inside with respect to time. And right now I'm making the assertion that that rate of change is greater than 0 because I see that all the Poynting vectors point into the box. The Poynting vector would be defined at every point on the surface. How would you calculate it? Well, let's look at this point, for instance. You would find the electric field right there. You would calculate the magnetic field right there. Then you take their cross product and divide by mu naught. Whatever that number is, that's really the intensity. That's the rate of flow of energy per square meter at that point in space. On the other hand, if all the Poynting vectors everywhere on the surface pointed outward, that would indicate that energy was flowing out of the box. And so the rate of change of energy inside the box would have to be a negative number. Powerful theorem, the Poynting theorem. A third example would be if the Poynting vector were a uniform vector field. That would indicate that the same amount of energy flowing in the left side of the box every second is also flowing out the right side. Whatever goes in goes right back out. So there's no net accumulation or loss of energy inside the box. Now, it doesn't have to be one of these three situations that I looked at. You could also have this vector on the right side be a little longer, which indicates that more energy is flowing out the right end than is flowing in the left end every second. If that were true, then you would be losing energy inside the box. Now, the actual statement of the Poynting theorem would involve a surface flux integral. If you've taken vector calculus, you've actually seen that. It's not that bad, but I'll leave that out for our purposes. One of the coolest things I've seen with the Poynting vector, and this is probably a simple example, but anybody who's taken a class on circuits or electricity and magnetism knows how to calculate the current through a resistor that's wired to something like a battery. And you also know how to calculate the rate of energy dissipation or power dissipation in the resistance. You know, all that electrical energy that flows through the resistor gets dissipated as thermal energy. So we know that I squared R is the so-called joule heating inside a resistor through which a current I is flowing. But you can also take a more abstract view and ask, well, where is that energy coming from? How does the energy get from the battery to the resistor? I mean, you could say, well, it flows through the wire, but is it really flowing through the wire? Is all that energy really just restricted to the volume within the wire? Because the wire is pretty skinny. And it's not like when you throw a baseball, you can transfer energy by having mass in motion. The electrons themselves weigh very little. So as they flow through that wire, you know, there's no tangible kinetic energy that they have. Where is the energy? Well, perhaps it's in, I say perhaps, but of course that's what I'm asserting. The energy is in the field, and you can show that mathematically. So since this is not a class on electricity and magnetism, I won't go into any detail here, but maybe you gleaned enough from the presentation about E and B fields to have known or to have noticed that if a current is flowing this way through a wire, in this case a resistor, there's a magnetic field that circulates around it. So these green vectors show you the magnetic field curling around the wire. Those of you who have taken electricity and magnetism, you know about Ampere's law. And we've got a conservative electric field that points from top to bottom. See, the plus terminal of the battery is here, the minus terminal is here. So the electric field points down, a lot like gravity. This battery does something kind of like if you had a high cliff with rocks at the bottom, and you can imagine some workers picking up rocks and carrying them to the top of the cliff where they're now endowed with gravitational potential energy. That's a lot like what a battery does. It takes electric charge and pumps it uphill. and the electric field points down, much the way gravitation or the gravity field points down. Okay, so the red vectors are the electric field. Now we can use the right-hand rule and the definition of the Poynting vector to see the direction of energy flow. So I put in my my mind here, I'm putting my 4 fingers along the electric field, which is the red one. I'm curling them into the magnetic field, which is the green one, and I find that my thumb points along the blue vector. So evidently, this particular configuration of E and B fields suggests a Poynting vector that's pointing towards the resistor. So we could even put an imaginary surface around the resistor. I could have made it bigger and actually given it the same diameter as this circle here. Maybe that's what I should have done. So imagine a cylinder with this diameter, and you would find that power is flowing into that volume. So this dotted circle here could be redrawn at the surface of the resistor. The same argument could be made about the directions of the field vectors, and you would find that the Poynting vector is actually fluxing through the surface of the resistor. So rather than think about energy flowing down the wire and into the resistor where it gets dissipated as thermal energy, you can think about the energy flowing in through the surface of the resistor from all directions. It was in the field surrounding the resistor. In fact, it's even flowing in space in all directions from the battery to the resistor, because you could repeat the same argument over here with the battery. The current's going clockwise around this circuit. So over at the battery, it's going from bottom to top. The current is flowing upwards. And that's why the green vectors now point this way. They point counterclockwise around this circle instead of clockwise. So use the right-hand rule to figure out the direction of the Poynting vector, and you'll find that it points out of the surface. So electromagnetic energy is flowing out of the battery, away from the battery, transiting through space. I'll let you examine this diagram and see if you can make sense out of it. You could use the direction of the current in these wires to infer the direction of the magnetic field near them. And you would find, yes, the electromagnetic energy makes its way from the battery through space over to the resistor. It's just amazing. When you do the calculation, if you calculate the value of S on the surface of the resistor and you do the flux integral right here to find the total power, which is, or I should say the total energy, which is entering the volume of the resistor every second, you get the same number that you would get if you just used basic circuit theory, I squared R. So this formula, this comes from Kirchhoff's laws. I'm sure this was known in the early 1800s. Well, it was another 50 to 100 years, I don't know exactly, but later that Poynting wrote down his theorem, and we find that we get the same number. So lots to think about there. That's a very rich picture. Whoa. Whoa, man. Let's look a little more carefully at the value of the Poynting vector in time for the specific case of sinusoidal progressive waves. Remember, waves don't have to be sinusoidal. In fact, most of the time they're not. If the waves traveling into your modem or your Xbox or your PlayStation from the internet company were sine waves, they would contain zero information, and that wouldn't be very useful. So most of the waves around us all the time have a much more complicated dependence on position and time. But you can build all of those waves up out of sine waves, which is why we study sine waves. Okay, so each of these progressive waves is sinusoidal. And now instead of just a number out here, previously it was the amplitude A, now we've got a vector out front. So how does that work? At this position, at this point in time, this is a snapshot graph, the electric field at this point on the axis points this way with a strength given by the length of this vector. And you can see that that's the max strength that it's going to have, because a moment later, this part will be right here. And that means the field strength will be a little bit less. So it's still an amplitude in a sense, but now it carries the information about the direction too. The amplitude is an actual vector. And it's the sine function here, which makes the value of the field change in time. Let's evaluate it. Let's just pretend that this is the origin. It's not in the picture. Over here is the origin, but let's pretend this is the origin. And that would mean that the x coordinate is 0. So you plug in 0 right here, and you've got the sign of negative omega t. So as time advances, this sine function goes between 1, negative 1, 1, negative 1. What would negative 1 times E naught look like? Negative 1 times this vector E naught would just flip the vector to the other side. So hopefully you can see that the field at this point is going to point this way and then shrink, and then it'll point this way and grow until it's down here. Then it'll shrink. It's just flipping back and forth. The B field is doing the same thing. So this is no different from the progressive waves we looked at previously, except for the fact that the amplitudes are now vectors. Okay, and by the way, did you notice I'm being very careful with my notation here. The electric field depends on the position where you're evaluating it and the time. If you go to a different place, you're going to have a different E field probably. If you look at the E field at a different time for the same position, it will probably also be different. So this vector field depends on time. Okay, well, when you look at the magnitude of the Poynting vector, notice I did not put the arrow here. So I'm talking about the magnitude of the Poynting vector, and I'm emphasizing that that magnitude depends on time. Let me go back here. So E points this way, B points this way. The Poynting vector, if you use the right-hand rule, points to the right. So if you evaluate the length of that vector at some particular place on the axis and look at how it changes in time, you would find this. See how there's no vector symbols? This is the magnitude, and it clearly depends on time. In fact, that time dependence involves the square of a sine function. What does the square of the sine function look like? Well, if the blue curve is a sine wave, the red curve is sine squared. See how it turns all the negative quantities or negative values into positive values? So what would this look like in time? Well, most electromagnetic waves that we're familiar with, radio waves, ultraviolet, visible light, involve extraordinarily high frequencies. They're way up here, 10 to the 13th, 10 to the 14th. In fact, the visible region you can see is between 10 to the 13th and 10 to the 15th. So that's a good number to memorize. The frequency of visible light is way up there at 100 trillion. This formula is telling us that the magnitude of the Poynting vector is oscillating something like 100 trillion times per second. It's going from its maximum to its minimum, to its maximum to its minimum, hundreds of trillions of times per second. And you'll notice that for every period of the E&M wave, this is a full period in time, the Poynting vector actually oscillates twice since we've got a sine squared. So the, what's the word it flutters. That's the word I was looking for. The rate of energy flow at a particular point in space, it's fluttering very rapidly. It's like there's this spurt of energy at that point and then nothing, and then another spurt of energy and then nothing. And we're talking about hundreds of trillions per second. And that means if we go back to a formula from a previous week, this is a slide you already saw in another presentation. We talked about the intensity of the power radiating from an isotropic source, whether it's sound waves or E&M waves. This time we're talking about E&M waves. We arrived at this formula. This is the power output of the source. That's the number of joules per second coming out of the source. This is the surface area of that imaginary sphere at radius r from the origin, or from the source, I should say. So if we'd like to evaluate this intensity for an electromagnetic wave, which intensity are we talking about? Again, if we go back to the graph, oops, I'm going the wrong way. Which intensity are we talking about? This one, this one, this one? Because the flow of energy turns on and off, trillions of times per second. So how do you pin that down? Which number are we supposed to pick if it's going through this whole range many, many times per second? Well, you could probably figure out that we should define some sort of average. What's the average flow of energy per unit surface area per unit time. Well, don't let this confuse you. I'm using the letter X right now. Don't even think about that as the x-axis. That's just a general variable x. I'd like to know what the average of the sine function is over one complete period. You could say period or wavelength over one complete cycle of the sine function. Here's how you would do that. If y represents our function sine squared, then the average value of y over a full cycle would be the integral of that function over the cycle. See, I'm integrating sine squared, which is the function, from 0 to 2 pi. So integrate the function over the whole cycle and then divide by the width of that. Did I say the width of the cycle, the interval? And I believe in calculus, they call this the mean value theorem for integrals. I'd have to look that up. But this is really the math definition of the average value of the function. You remember what integrals give you, right? They give you the area under the curve. Basically, take the area under the curve, that's the integral, and then divide by the width of that area, and that would give you the height of an equivalent rectangle. I'm sorry I don't have a graphic for you, but you can imagine a rectangle here that has the same area as the area under this curve. And the height of that rectangle is the average value of the function. Well, you could probably guess. Since sine squared goes from 0 to 1, what do you think the average value of this function is? What's the height of the equivalent rectangle? Just from looking at that picture. You could do the integral if you wanted. You would find that it's 1/2. And I'll go a step further with this because many of you will take classes where you see this again in the future. I would just memorize that. The average value of sine squared or cosine squared over a full cycle is 1/2. But if you look at the symmetry here, that would also be true over half a cycle, right? If you just calculate the average of this one hump, it should be 1/2. And that's even true of a quarter cycle. I don't think you can go any less than that. So that's my assertion. If you look at the average value of sine squared or cosine squared over one quarter cycle, one quarter cycle, which is a half hump, you get the value 1/2. Okay. So there it is. This red line represents the height of the equivalent rectangle. How can we use that in the task at hand? And here I'm stating it in terms of time now. So the average value of sine squared over a full period is 1/2. So let's average this over one full period in time. If you're hanging out at a particular point in space and this energy is flowing past you because of the electromagnetic wave and it's very fluttery, sometimes the energy is spurting past and sometimes it's not. How do you find the average in time? Well, we've just determined that the average value of sine squared over a full period is 1/2. And so there we go. S bar, that means the average value in time, the average time value, or I should say the time averaged value of the magnitude of the Poynting vector picks up a factor of 1/2. And then I did the same trick here. The reciprocal of mu naught, that's the same as c squared times epsilon naught. You can look back at the formula to confirm that. And then one more thing, remember, for an electromagnetic wave in vacuum, the strength of the B field is the same as the strength of the E field divided by C. So let me make that substitution. And this is what we were working towards. This is a formula that you'll find in your book. That's a formula worth putting on your note card. And that is what we call the intensity. So it's kind of subtle. If you were to define intensity as the instantaneous value of the watts per square meter, you would find that it's fluttering trillions of times per second. That's super inconvenient. You know, if you're looking at how much energy flows through a surface over a period of 1 minute, you don't need to know what's happening from 1 trillionth of a second to the next trillionth of a second. So smooth out all those flutters over a tiny time scale. Let's just calculate the average value of the Poynting vector in watts per square meter. That's what we call intensity. So intensity is that smoothed out value of the Poynting vector in time. Definitely throw this on your note card. Look what you can do with this formula. If you really did have an isotropic radiator, and antenna towers are not isotropic radiators, but suppose they are, you could use the inverse square law to find the intensity at any point in space. So if, let's say you live 30 miles from an antenna that's on top of a skyscraper in downtown Los Angeles, and you happen to know that the transmitting antenna is a 50 kilowatt antenna, because a lot of antennas for radio stations are 50 kilowatt antennas. Take that 50 kilowatts, divide it by the surface area of that imaginary sphere, and now you've got your intensity at your house in watts per square meter. All you have to do is plug that value in here for the intensity. We know the speed of light. We know the permittivity. So we can solve for the strength of the electric field. That's pretty cool, right? If you're talking about a sinusoidal progressive wave, and it probably applies even if the wave you're talking about is a superposition of a bunch of different sine waves of different frequencies. I don't want to make that assertion quite yet, but if you happen to know the intensity and it's a sinusoidal electromagnetic wave, you can easily calculate the strength of the E field and vice versa. And that's all for now.